when engineers, scientists, analysts, as well as other professionals model their work with functions, they often have to compose the functions together. And when they wish to find the optimum value for the composition of those functions, they need to use the chain rule to find the derivative. Hi, my name is Tom Atwater, and that's the topic for today. Let's take a look at the definition of the chain rule. The chain rule says, if f is differentiable at the point u, which equals g of x, and g is differentiable at x, then the composite function f of g of x is differentiable at x, and f of g prime of x, that is the derivative of f of g of x, is equal to the derivative of f of g of x times the derivative of g of x. Let's look at what's called the Leibniz notation for the chain rule. The Leibniz notation is if y equals f of u and u equals g of x, then the derivative dy dx is equal to dy du times du dx, where dy du is evaluated at u equals g of x. Now, if we look at the composition formula for the chain rule, we can think of it as taking the derivative of the outside function, where it's evaluated at the inside function, and then multiplying that times the derivative of the inside function. I think it's best to look at some examples to explain that in further detail. So let's say we want to find dy dx, and we have y equals x plus the square root of x, quantity raised to the -2. We also have y equals sine raised to the -5 of x minus cosine cubed of x. Let's take these one at a time, and first we'll find the derivative of this. So we have y prime equals, we bring down the -2, and then we have x plus the square root of x raised to the -3. So that's like taking and differentiating the outside function. But now what we need to do is multiply that times the derivative of the inside function. The inside function is this x plus radical x. The derivative of x is 1 plus the derivative of the square root of x works out to be 1 over 2 radical x. And we'll just leave it in that form, although certainly you could simplify that. Now let's take a look at the one that had trig functions in it and apply the chain rule to that. So we have y equals sine to the -5x minus cosine cubed x. So y prime is going to be the -5 times sine to the -6 of x, subtracting 1 from the power. But now that's like the outside function, because now what we have to do is take the derivative of just sine x, because sine x is the inside function here. And so we multiply times the derivative of sine, which is cosine. Then we have to take care of the cosine cubed function. So that's going to be -3 cosine squared x. But again, that's like the outside function. Then we have to take the derivative of just sine x, I'm sorry, the derivative of cosine x, which is negative sine x. We can simplify that just a little bit. We can write it y prime is equal to, and in the first case, nothing simplifies in that term. So we have -5 sine to the -6 x times cosine x. But now what we can do with the second term is we have a negative times a negative. So that's going to be plus 3 cosine squared x times sine x. And that's our derivative using the chain rule twice, once for each term. Let's try another example. Let's take the example of finding the value of f of g prime at the given value of x. And we have the function f of u is equal to 2u over u squared plus 1. We know that or we're told that u is equal to g of x, which is equal to 10x squared plus x plus 1, and that x itself is equal to 1. So the important information here is that we have u is g of 0, because x is to be evaluated, g is to be evaluated when x is 0. And when we plug that in, we find that g of 0 is 1. And that's where we're going to evaluate this derivative. But first, we have to find the derivative, f prime of u. We have to apply the quotient rule. So we have to take u squared plus 1 and multiply it times the derivative of the numerator, which is 2. And then we subtract the numerator times the derivative of the denominator, which is 2u. And that all goes over u squared plus 1 quantity squared. We definitely need to simplify the top some more, so f prime of u will equal 2u squared plus 2. Then here, when we multiply, we'll get minus 4u squared. And that's all going to be over u squared plus 1 squared. And then finally, we can combine the negative 4u squared and the 2u squared. And that's going to give us negative 2u squared plus 2 over the denominator u squared plus 1 quantity squared. Now we need to evaluate this, remember, when the value of u is 1. So when we do that, notice what's going to happen. This is going to turn out to equal 0 because we're going to have negative 2 plus 2. So therefore, f prime of u is equal to 0. Let's try another example with more links in the chain. Let's take a look and apply the chain rule to the function y equals 1 plus cosine squared 7x all cubed. So the first thing you'll notice is we've got to take care of the power. So y prime is going to be 3 times 1 plus cosine squared 7x raised to the 2. Then we have the inside function, 1 plus cosine squared 7x, so we have to take the derivative of that. The derivative of 1 is 0, and we have to bring the 2 down in front. So it's 2 cosine 7x. And of course, when we subtract 1 from that exponent of 2, we get an exponent of 1, which we don't bother to write in the cosine. Now what we have to do is take the derivative of the inside function, which is cosine 7x. And the derivative of cosine, of course, is negative sine 7x. And there's one more function inside here, which is the function 7x. And we have to take the derivative of that now. And the derivative of 7x is, of course, 7. So we had to use the chain rule a number of times in this particular problem in order to find its derivative. We could simplify that a little bit, but in terms of what we're interested in is the chain rule, so I'm going to leave that just the way it is. We can use the chain rule to find the slope of a curve given to us parametrically. Let's take a look at this formula. If x and y are a function of t, that means they're given to us parametrically. Then, if all three derivatives exist and dx dt is not equal to 0, then what we can say is dy dx, the derivative of y with respect to x, is going to equal dy dt divided by dx dt. Let's try an example where we are going to find the derivative of curves given to us parametrically. Find the equation of the line of the tangent to the curve defined by, parametrically, x equals secant t, y equals tan t, and the range for t is negative pi over 2 to pi over 2, and at the point square root of 2 comma 1, where t is equal to pi over 4. So we need to find the derivative using that formula for parametric derivatives. So let's get a clean blank screen, and so what we're looking for is dy dx, which is going to be dy dt divided by dx dt. And remembering that y was equal to the tangent, and that the derivative of tangent is secant squared, the top then is secant squared t. Now, x was equal to secant t, so the derivative of secant t is secant t times tan t. And you could simplify that, and actually it simplifies all the way down to cosecant of t. We're supposed to evaluate this where t is equal to pi over 4. So we want cosecant pi over 4. And the cosecant of pi over 4 is equal to the square root of 2. So now we know that that's the slope of this tangent line. We were given that this would go through the point square root of 2 comma 1. So our equation becomes y minus 1 equals the square root of 2 times x minus the square root of 2. And then we can simplify that a little bit by distributing the 2 and bringing that 1 over. So we have y equals the square root of 2x, and then square root of 2 times the square root of 2 is going to be minus 2, and then we're going to add 1 to that, so we get minus 1. So that would be the equation of the tangent to the curve, finding it by using the derivative parametrically. Well, now it's time for you to try a problem. So I'm going to give you a problem that involves parametric equations as well. Find the equation of the line tangent to the curve defined parametrically by x equals 2 cosine t, y equals 2 sine t, at the point where t is equal to pi over 4. Pause the video while you work on this problem, and when you're finished, restart the video to check your solution. Hey, let's find out how you did on this problem. This was the original problem that I gave to you, so it's given to you parametrically, so we have to use the formula for the derivative of parametric, and that is dy dx equals dy dt over dx dt. And in this particular example, you were told that y was equal to 2 sine t. So the derivative of 2 sine t would be 2 cosine t. We were told that x was equal to 2 cosine t. So the derivative of cosine is negative sine. So this would be negative 2 sine of t. And that simplifies all the way down to negative cotangent of t. We were supposed to evaluate this when t was equal to pi over 4. So what we're looking for is negative cotangent of pi over 4. And negative cotangent pi over 4 is equal to negative 1. So that's our slope for the tangent line. Now, in terms of the point, we weren't told any particular point that lied on this curve, but what we know is t is equal to pi over 4. So let's plug t equals pi over 4 back into the original equations, which are x equals 2 cosine pi over 4. And the cosine of pi over 4, of course, is the square root of 2 over 2. So this is 2 square roots of 2 over 2. Those cancel to 1, and we get that x is the square root of 2. Well, when we go to evaluate y is equal to 2 sine of pi over 4. But the sine of pi over 4 is also the square root of 2 over 2. So 2 times the square root of 2 over 2, we already know, is the square root of 2. So that means y is equal to the square root of 2. So now we have a point that we can plug into the point-slope formula and say that the equation is y minus the square root of 2 equaling negative x minus the square root of 2. And we can simplify that a little bit and say that y is equal to negative x and then plus 2 square roots of 2. And that's the equation of the tangent line of the parametric curve where t is equal to pi over 4. In this lesson, we studied the chain rule and looked at many applications of the chain rule. Be sure to work the exercises that your teacher assigns, and we'll see you next time.